Hello boys and girls, it's Miss Alvarez again. I'm here to talk to you today about the solar system. Now, throughout history, astronomers have had lots of different ideas as to how the solar system actually worked. They didn't even know there was a solar system hundreds of years ago. In fact, they thought that the Earth was the center of the solar system. This is called a geocentric model. Geo meaning Earth and centric meaning at the center of. So they thought that everything in the universe revolved around the Earth, that we were the center of everything. But throughout the years, we've learned differently. We have found that our sun is actually the center of our solar system, and that they are billions of solar systems in the universe. We can't even count all of them. We don't know all of them yet. In fact, we can't see far enough to see everything. So there's no telling what's actually farther than what we can see right now. We do know, however, that we revolve around this. Now, revolutions mean that we travel around another object. Now, we revolve around the sun, but our moon revolves around us. Now, we talked about rotations last time in day and night. And rotation means that I'm taking the Earth and he is spinning and spinning and spinning about that 23.5-degree angle, spinning and spinning and spinning and rotating and rotating. And now the sun being at the center of our solar system means that we have a heliocentric model. And helio means sun. Centric, again, means at the center of. So all of the planets in our solar system actually revolve around the sun. Now, the sun is where we get all of our energy from as well. We know that energy cannot be created, it cannot be destroyed. But the sun has lots and lots of processes going on. It gives us heat, it gives us radiation, which our planet desperately needs to support the life that it has on it. Okay, the closest planet to the sun is Mercury. Now, Mercury is the smallest planet in our solar system. It's not the hottest, though. You would think because it's closest to the sun, it would be the hottest planet, but it's not. Venus is actually the hottest planet. So, Mercury being close to the sun, we know that it barely has an atmosphere because of the solar winds that come from the sun, constantly bombarding Mercury. We know that Mercury's atmosphere is being blown out, but we have winds also that are bringing it back in. And we do have radioactive decay that continues to provide some kind of atmosphere within Mercury. Now, Mercury was named after the Roman messenger to the gods, and it's first seen in historical documents mentioned by the Sumerians in about 3000 BC. Which was a very long time ago. We're talking 5,000 years ago, plus. Okay, the second planet from the sun is Venus, and Venus is Earth's sister planet. And it's known as Earth's sister planet because it's roughly the same size as Earth, about 4/5 the size, so a little bit smaller than Earth is. It's also the hottest planet in the solar system. Venus is also the second brightest object in the sky. So we can see Venus during the day sometimes, and definitely at night. The only object brighter than this is the moon. Now, of course, the sun is what's giving us that light to reflect off of the surfaces of the moon and off of Venus. They don't create their own light, but they are very bright compared to the other things around us. Okay, Earth is the third planet from the sun, and being the third planet from the sun, it is just the right distance from the sun to have a support of life system. We have lots of water as well, but we also have an atmosphere, and most of our atmosphere is made up of nitrogen. I know that we talked a lot about the need for oxygen whenever we were doing our life units, but nitrogen makes up about 78% of our atmosphere, where oxygen is about 21%. Then we have argon and carbon dioxide. Now, I know you've heard about carbon dioxide and its emissions of greenhouse gases. The greenhouse gas, carbon dioxide, does help to heat up our planet, and it's not a bad thing. You need carbon dioxide to heat up a planet. We don't want to get rid of all of our carbon dioxide, but when you add too much carbon dioxide to our atmosphere, we trap too much heat from the sun, and that makes our planet hotter than it needs to be to support life here. So we'll have stronger storms, you'll have stronger currents in the ocean, you'll have more melting of the ice caps. You can also have more forest fires because it gets hotter, obviously, more desert formation and things like that. We don't want so much carbon dioxide in our atmosphere that it causes that to change for our planet, but we don't want to get rid of all of it either. And believe it or not, the planet itself emits carbon dioxide. Whenever volcanoes blow, it emits lots and lots of different types of gases, carbon dioxide being one of them, as things are burning up. So the planet itself does account for a good percentage of the carbon dioxide emissions into the atmosphere, not just people. We just tend to put things in the atmosphere that aren't naturally going to be there through the use of our machines, namely our cars and factories and things like that. Okay, this is Mars, and Mars is known as the red planet, obviously because of the color of the surface. Now, it takes roughly 1.9 years of Earth time for Mars to make one orbit around the sun. So it's almost 2 years going around the sun for Mars to go around one time. So it does have a larger orbit than we do, simply because it's farther away from the sun than we are. Okay, so the ones we've gone through so far, Mercury, Venus, Earth, and Mars, are the 4 planets that are known as rocky planets. And the rocky planets are also known as terrestrial planets, and it's just like their name means. Rocky, obviously made out of rocks and metals. Terrestrial simply means land. So we've got rocks and metals and things like that just from the name. These 4 planets are the closest to the sun, and they do have most of their composition being that of rocks and metals. Now, as we enter into the next phase of our solar system, we're not going to see the same composition for the most part in the planets. We're going to see more gases forming instead of simply rocks and metals. And this does change, especially the volume of the planet, because these things can only be compressed so much, and they are closer to the sun, so they're denser, more solid, and as we get farther from the sun, the gravitational pull of the sun is less than it is closer to the sun. So the closer you are to that large object that has that gravitational pull, the stronger the pull of that object is. So those gaseous planets on the outside are composed, yes, of rocks and metals, typically at their cores, but then they're surrounded by this gas. And we know that gases can be compressed, or they can be, that's right, released. So whenever those gases expand, they give a greater volume to the outer planets than the inner ones. Okay, so what we're going to be doing here is creating a model, and science is all about models. We always want to show what we understand about the situation because it's real. Now, we're going to use something called astronomical units. Now, an astronomical unit is simply a unit that is comparing how far the Earth is from the sun to how far that other object is from the sun. So, one astronomical unit is about 150 million kilometers, because that's how far the Earth is from the sun. A little less than 150 million, but right at 150 million rounded up, okay? So the distance of the Earth from the sun is one astronomical unit. So whenever I'm doing my placements of all of the different planets, I'm going to compare that planet to the Earth. Okay, and you can see here how we're going to convert our scale. So we have one astronomical unit is equal to 10 centimeters, because I've chosen 10 centimeters to be the distance on my model for an astronomical unit. We need a conversion equation, and my equation is x times 10 equals c. Now, we have two variables in this equation, the x and the c. But we have to be able to find one variable by performing mathematical operations within the equation itself. So my x is a number of astronomical units. So whatever my astronomical unit is for that planet, I'm going to substitute my astronomical unit for my x here. C is what I'm solving for, and C is the centimeter distance in my solar system model. So whenever I plug in these numbers into my conversion equation, I'm going to be able to solve for the number of centimeters I will need in my model. Okay, you can see here where we have the first model of the rocky planets, and the astronomical units go from the middle of the sun to the center of the planets. So from the middle of the sun to the center of the Earth, we've got 10 centimeters. From the middle of the sun to the center of Mercury, it's 3.9 centimeters because it's 0.39 astronomical units. From the center of the sun to the center of Venus, it's 0.72 astronomical units, and therefore 7.2 centimeters. And from the center of the sun to the center of Mars is 1.52 astronomical units. Therefore, the center of Mars should be positioned at 15.2 centimeters. Now, obviously, these planets are not going to be bundled together like this in orbit. They're going to be around the sun in different positions. This is just a model to show you how far they are compared to one another, typically from the sun. Okay, Jupiter is the fifth planet from the sun, and it is the largest planet in our solar system. It's known for its red spot that we believe is a storm that's been going on for centuries. It also has a large amount of moons, which is, I think, 53 confirmed, and then several that have not been confirmed yet. Okay, the sixth planet in our solar system is Saturn, and it's known for its beautiful rings, its icy rings, and also for landscapes of its moons. It's surrounded by more than 60 known moons and has beautiful, beautiful landscapes. It has water sprays and methane lakes, smoggy areas, and lots of gases that are deadly to us but beautiful to see with a telescope. Saturn also rotates extremely quickly. It finishes one complete rotation in about 10.7 hours, which is less than half of one of our days. So, very quick rotation. However, it does take a little over 29 years for it to revolve around the sun, and this again is because of how long it actually has to travel, because it is so far away from the sun to start with. Okay, Uranus is actually the seventh planet from the sun, and it rotates on its side at about a 90-degree angle with its axis. So you've got its axis here, and then it's rotating sideways. very different from the rest of the planets in the solar system. Uranus is also mainly gas, just like Jupiter and Saturn, but different kinds. And we do believe that Uranus has actually been emitting gases into the atmosphere. We're not sure exactly how much, but scientists have discovered some leaks going on. And Uranus has almost the same gravity as Earth. It's a little bit less at about 80%-ish. So you would weigh almost the same on Uranus as you do here on Earth. Okay, eighth planet is Neptune, and it is the only planet in our solar system that is not visible by the naked eye. So you do need a telescope to see Neptune. It is an icy giant. Okay, Neptune also has a length of a year being 60,190 Earth days. So by the time you made one revolution around the sun, if you were on Neptune, you would be almost 165 years old. We have 5 dwarf planets that are in our solar system. One they classified as a planet when I was a kid. It's Pluto. And Pluto does take over 90,000 Earth days to make one revolution around the sun. On NASA's website, it is not designated as just a planet, but it is a dwarf planet. So NASA has some really great interactives on their website. If you want to go on there and look at all of these different dwarf planets and all of the different interactives that they're showing for our solar system, it could be pretty good information for you guys. Now, I'm going to do the same thing with these planets that I did with the rocky planets, and that is show you a model based on astronomical units to see how far they are from one another. Okay, starting on the rocky planets, to meet our first gas giant, we have to move very great distance to 52 centimeters. And this is 5.2 astronomical units from the sun. And then to get to the next one, Saturn, it's another great leap. 9.54 astronomical units, 95.4 centimeters. Moving on to Uranus, 19.2 astronomical units, 192 centimeters, and then continuing on to Neptune, which is right at 300.6 centimeters from the sun to the center of the planet. And now I'd like to challenge you to make your own model of our solar system. You don't have to use the method I did. You could use beads on a string or knots on a string. Or you could make plates, draw the designs of the planets, and then put them outside at different intervals that go along with their astronomical units. You can use any unit you like as your astronomical unit and then use proportion from there.